So a lot of times we focus on the operational aspects of mathematics in our first and second year math courses. What that means is you probably know exactly how to calculate the Taylor series, or at least at some point you had done enough problems that you knew how to calculate Taylor series very quickly. But you may not be as familiar with the properties and application of the Taylor series. So this is what I mean by operational aspects, right? So one of the important things that you need to understand about how these kinds of functions work, and actually it's a deep mystery when you think about it. Let me make a point here on this object, so I'm going to make a point there. So I must say, if I had this tool when I was studying math, I would probably have done better. Okay, and I'm just going to put an order here in. Yes, right. Okay, so that's amazing, right? That's now a first order Taylor series expansion, which is on that sine of s function, and I can kind of increase the order and kind of move it around really easily. Let me just actually set this. See, I don't understand it, but there seems to be no reason why you wouldn't just use the one. Okay, there you go. Right. So, when I say it's kind of surprising that Taylor polynomials work the way that they do, is look at that function. I've taken a sinusoid, right, and only at the point that you are making the approximation at. In other words, you need the value, the first derivative, the second derivative, the third derivative, and all the derivatives, right? But it's all very local. And so this is why I'm saying it's actually quite surprising that knowing information just about the behavior of the function right here is going to enable me to predict that that function looks the way that it does far away from the point of approximation. Specifically, it's weird that I can only use the values around there and predict that this is going to go up and then down. It's going to kind of oscillate all the way there. How does that even work? Is that something that works for all functions? What are the kinds of functions that Taylor series actually work for? And in your experience, Taylor series by and large have converged. In other words, if you have enough order, right, the Taylor series converges over the entire real line, which is a spectacularly surprising thing. That just knowing all the information around one point in the function enables you to predict the value of that function at some plus 1,000 value. Especially knowing what we do, right? Knowing that, for instance, I could easily define this function. I could define this function to be sine between here and here, but then like a constant above 5. Right? That's a perfectly reasonable function definition. We've done that. We've said, let's take a ramp function which is 0 to the left of the line and t to the right of the line. Now, it shouldn't surprise anybody that Taylor series wouldn't converge on that function. Does that make sense? So something like the ramp function, something like this function, right? So that function over there, which is this straight line over here, but straight as a constant over there, we wouldn't expect Taylor series to converge. Firstly, it only has that one non-zero derivative, right? So it's a constant. But if I do an approximation over there, it'll be a straight line. If I do an approximation over here, it'll be a straight line. So it doesn't converge globally. And so very quickly we realize that the functions for which Taylor series converge are special. So things like the sinusoidal function is not. So these functions for which Taylor series converge, by the way, have a name. They're called the analytic functions. And so you may have heard this being thrown around like, oh, do I have an analytic solution? But analytic functions are functions that have convergent Taylor series. Taylor series that converge to the function over the real line. And it's important to understand that this is not true for all functions. It is true for some very special functions. Now, why is it that these are the functions that you see everywhere? Because they are special. Because they are a little bit like a polynomial. I've spoken about this before. The functions that we really like are linear functions, right? Linear functions are amazing because they have a single solution. Even systems of linear equations have a unique solution. We never worry about whether we will be able to find the solution. We can solve linear systems really easily. Polynomials are a little bit harder, but still really easy because we have the fundamental theorem of algebra, which means that we know a lot of things about polynomials, right? We know how many roots they will have. We have strong methods of finding those roots and so on, right? Then, kind of the next step up is the analytic functions, which are effectively like polynomials with infinitely many terms. And those functions are all the kinds of functions that we can typically do really easy number math with, right? So we can easily say, if I have something like the sinusoid, who here, by the way, knows how sines are calculated? So what I mean is, if in a very short amount of time, like what happens on your calculator when you type sine 5 for you, okay? The way that your calculator probably uses is that it uses a power series, either a Taylor series or some other power series that converges rapidly with a small number of terms to the thing that you're trying to calculate, okay? And so there are only a limited number of functions that have nice convergent power series, and those are the things that we find the most useful, because at least we can actually calculate those values, right? So there is something, the reason why I'm talking about all of these things is that you have used approximating functions basically since you were able to do calculations with numbers. In fact, it's been the default way that you've done calculations like forever. You just haven't really acknowledged it. So every time you do a calculation with your calculator, you're not doing an exact calculation, right? Every time you calculate the sine of 5 with your calculator, it is already doing like some kind of power series approximation to that function and then giving you the number from that. And it's not like letting that sum go to infinite, right? It's letting it go to 5 or something, just so that it gets enough digits. So this is the same for every single one of these functions that has convergent power series. So I want you to kind of just confront yourself with that truth, that these things are not globally good, right? They are locally good. And it is also surprising that they are as good as they are locally for the number of functions that we find useful. But I'm going to just zoom out, and I want you to see a very important property. This is a property of polynomials in general. But when I zoom out, it becomes very clear that polynomials of even order have this property that eventually both of the far behavior of polynomials, right, always looks like this. Has this behavior that when x gets big in magnitude, the polynomial gets big in magnitude. And you can imagine that this is not a great property when I'm trying to approximate functions like this sine function, which stays quite near to 0 for that entire real line. In fact, you could make the argument that y equals 0 is a better approximation of sine of x than any order of Taylor series, any finite order of Taylor series, if you look over the entire real line. Does that make sense? Right? So in terms of if I calculate the error by perhaps integrating the difference, right? Or the difference squared, so that we don't cancel out positive and negative errors, right? Taylor series have terrible behavior because they all have infinite error far away from the point of linearization. And we very soon find ourselves looking for different ways of making these approximations that have slightly different trade-offs. The thing that makes Taylor series nice, and just to kind of prove my point there, you can see that's the odd polynomial, right? So odd polynomials, they all go to different sides, and even polynomials, they all go to the same side eventually, right? So that's polynomial approximation, and we can see not great behavior far away from the point of linearization, and in fact it doesn't capture some very crucial characteristics, especially when we're talking about what is called far field behavior or asymptotic behavior, right? So I'm going to switch over to SymPy now and just show roughly the same thing, slightly less interactively. So here we have basically the same idea, just the sine function approximated by various orders of Taylor series, and zooming out we see rapidly that they become very large. Now, one of the important things that you need to understand about Taylor series, I've spoken about this before, this expression is chosen in such a way so that the derivative of that polynomial is the same at the point of approximation for any arbitrary chosen derivative. So in other words, if I do this for one term, I will match, or if I do this for 0, if n is equal to 0, right, it's very clear to see that I'll end up with a function value equal to the function value at the point of linearization. Right? Just the function value by itself. Because I'll just end up with the function value. So that'll be, so if n is equal to 0, I'll end up with f to the 0. That's supposed to indicate like a n derivative, right? So a 0 derivative is just the function value at the point A divided by 0 factorial, which is 1, multiplied by this to the power 0, which is also 1, and so I just have the function value by itself. Okay, if n is 1, the constant gets derived away. If I try and match the first derivative, right, I'll have that term there, and I'll have n equals 1. N will be the first derivative divided by 1 multiplied by x minus a, so I'll just have x to that first multiplied by that first derivative, so I know that I have a first order function which has the same derivative at the point of linearization. Does that make sense? Okay, so that's the classic version of this. That's really easy to visualize, is that, you know, like when we do linearization, we match the function value and the derivative, and it's very clear to see that that's a tangent line, right? But for a second order derivative, I'm now matching, or for a second order Taylor series, I'm now matching the function value, the first derivative, and the second derivative. In other words, it's got the same curvature at that point. If I do a third order, I'm matching the first and second and so on all the way to the second order. Okay, so that is, if I were to think about like what defines Taylor approximates, that's for me the defining characteristic of a Taylor approximation, is that it's this idea that I can take a polynomial and I can make a polynomial which, as far as I can make derivatives, matches the derivatives of the function that I'm approximating. That's really the key feature of Taylor polynomials. And it's matching at that one particular point. It's not, and there are other polynomials. If you're interested in math, you can maybe Google Chebyshev polynomials or the genre polynomials, which are approximants on different measures, right? So Taylor isn't actually trying to be an accurate approximation when we talk about the difference between the function and the approximation. So most of us would imagine that what you're trying to do is you're trying to get as close as you can to the function, right? If I want to approximate one function by another function, I want to make sure that their curves look like one another, right? And in fact, Taylor isn't even trying to do that. Taylor series are not chosen for accuracy of approximation. They are chosen for this other property, which is that they match the derivatives at the point of approximation. And they have this other wonderful feature, which is that to calculate another order of Taylor polynomial, I only need to add on the extra term. All the other terms stay the same. Other approximating polynomials do not work this way. So I could say, we could, for instance, say, let's try and minimize the error of approximation over a certain range. That's one of the things we could do. Or we could say, let's try and have the smallest maximum error within some range. That's another. And both of those choices lead to completely different polynomial approximations. And as it happens, neither of those polynomial approximations will match derivatives at a particular point. Right? It'll just have this property that will kind of smooth out the error. So Padé approximation is like Taylor approximation in this one thing that it is trying to do. It does the same as Taylor approximation in the sense that it matches the derivatives of the target function down as many orders as we want. it does it differently because it is not a polynomial, but rather a rational function. And because of that, it also lacks this other property, which is that you can simply calculate one extra term and just add that on, right? There's no relationship between the values of the parameters that you get, or the values of the coefficients that you get for the low-order Taylor or Padé approximation to the high-order Padé approximation, right? So if I wrote a Taylor series approximation, if I wrote one of these out like this, right, I could look at that and say, right, that's the quadratic term, that's the linear term, that's the constant term, and I could get a linear version of that by crossing out that term, right? So they share coefficients, in other words, right? So Taylor series share coefficients, but Padé approximations do not. So if I calculate the coefficients of a Padé approximation, a 1-1 Padé approximation, which means that I've got a first-order polynomial over a first-order polynomial, those coefficients I just need to completely throw away when I calculate a 2-2 or a 2-1 or whatever, right? So the bottom one as well won't necessarily be the same. So I've come up with this strategy which basically uses exactly that definition. I'm setting up the set of equations that I need to solve in order to match the derivatives of certain orders, right? So all I'm doing here is I've got the difference between the target of approximation and the form that I'm trying to approximate with, just zero derivatives, first order derivatives, second order derivatives. And so because I've got those three equations, in other words, I've got the function values must be equal, the derivatives must be equal, and the second derivatives must be equal. I've got three different equations. I happen to have three parameters, a, b, and c, and I can easily solve for a, b, and c. And so that's really straightforward. This particular one is so common, we will use it so frequently, that I definitely don't want you to use code to come up with that. It is right here in the formula sheet. Okay, so because we use Padé approximation of dead time quite frequently, it's one of those things that we can kind of just read off the table. Now, if you want to use a higher order Padé approximation, you've got the tools to do it in that notebook. But you just need to understand what we're trying to do is we're trying to make this approximation which just matches derivatives. Now, obviously, we've got more to think about than only how well the derivatives match. Now, we know that this is definitely true. We've constructed this rational function to match derivatives with the original function at the point 0. And so that we absolutely know is true. But if we take the same number of coefficients in a Taylor series, now notice here, the Taylor series has also three unknowns. You could do exactly what I did over there, up here. So this exact same procedure should give you exactly the same coefficients if you use the polynomial generator. If you just had A, B, and C over there, and then solved for A, B, and C, you'd get the same answer, right? It just happens to be that the Taylor series expansion in SymPy is a lot faster. Right, so the reason why we're going to all this trouble is because of this thing that I just said, that one of the big problems with Taylor series approximations is that they rapidly grow to very large values away from the point of linearization. And if we're trying to linearize around the point 0, and we have something that looks like an exponential function, exponential functions have this behavior that make them much different from polynomials. In other words, they move asymptotically towards that axis. In other words, specifically e to the minus something t will go towards 0, very, very far away from that axis. And so we know, if we just add this function over here, so that's, let's do the same thing over here. I'm going to change this to the exponential function. Right, so there we have our exponential function and our polynomial approximation, and we can kind of see that it doesn't really matter. It doesn't really matter how high the order goes. We can extend the little bit that it goes it stays near to 0, but then eventually, like all polynomials, it eventually moves away from it, right? Now, so if we just add our Padé approximation here, we see that that is significantly better. So at the point of linearization, which is 0, that approximation looks pretty rad. Actually looks better than quite a high order Padé. Let's just take the order down. So you can see we're better than the second order Padé, but so actually let's just get there. And we also have this wonderful behavior that we are stable. We go to 0 or we stay close to 0 when x is large. Now the downside is we do have a bit of a problem, and that is that there's an asymptote on the left. So we're not doing quite as well over here because we're quite far away from that function. So the Taylor approximation stays closer to the function when we have a very, very large value of x or very negative value of x, right? But in the positive x space, the Padé stays a lot closer. And so this behavior that we want a relatively stable response on the positive time side, right? Positive time is kind of where we want to live most of the time, and the Padé approximation for daytime has good positive time behavior. The bad stuff kind of happens with negative time, and we don't really often reach negative time in our studies. Okay, so that's good. Another thing that is also great about this approximation is the complex behavior. Now, this is now something that you haven't done yet, but obviously we are working with transfer functions, and we're trying to get that transfer function. We're trying to approximate the transfer function, which is a complex function. And so it's important for us not just what it looks like in a section on the real line, but actually over the entire complex plane. We want to get it as close as we can. And we can actually see that the Padé approximation, if you look at the area, the region of approximation, the phase behavior. Now, what I mean by the phase behavior is, look at the colors, right? 0 is over there. And so you can see that around 0, we see quite a similar behavior. We see the same kind of phase behavior, the same sequence of phases as we go through, as we do in the real function. But if you look at the Taylor approximation, we very rapidly lose that nice approximation, and especially here in the positive area, it's considerably worse behaved, right? So we can see there's lots of stuff happening over here because we've got those two poles in the Taylor series approximation. Why do we have two poles? Anybody? Second order Taylor series approximation, second order polynomial. Second order polynomial has two roots. Those roots are those two spots over there, right? So now here I will actually allow you, I believe this is already in the cheat sheet. If it isn't, I'll put it in, but I will allow you to use this generalized Padé approximation function that I wrote. This kind of does Padé approximation relatively systematically. Now, I don't make any guarantees for weird functions, but it seems to work pretty well for even relatively high order functions. So here's for instance just a high order polynomial, and we can see the Padé approximation actually does pretty well. Right, so up to now we've been speaking about approximations which are focused on the target function, and we've used it for transfer functions. So we've said, here's the transfer function of a daytime, this e to the minus s, and what if we want to approximate that by a rational function? Now, just to reverse a little bit further, I just want to remind everybody why we even want to do this. The main reason why we want to take that nasty e and approximate it by either a polynomial or a rational function is because exponentials, or functions that include sums with exponentials, are hard to solve. And remember, we're going to want to find roots and do systematic analysis of our functions And that's going to be a lot harder if I have s to the 10 plus e to the minus s as my denominator in my polynomial, right? Why? Because how many roots does that function have? Nobody knows, right? There's no guarantee. There's nothing like the fundamental theorem of algebra when I'm calculating the roots of functions that contain e's as well. The minute I have polynomials, I can tell you, oh, s to the 10, that has 10 roots. S to the 11, that has exactly 11 roots. I know exactly where they are. If I add an e in there, it becomes a lot harder. And this is one reason why we want to make these things simpler. So that's one reason why we may not want e's. We may also not want just higher order polynomials. Now, if this was 5 years ago, I would have said the reason why we don't want higher order polynomials is because it's hard to calculate the roots of polynomials. This is still relatively true, except that this is not your lived experience. It's just as easy to calculate the roots of a 10th order polynomial as a second order polynomial because you use the computer for it, right? But what is true, what will resonate with your lived experience is that inverting a high order Laplace transform in SymPy doesn't work. When I say doesn't work, it doesn't give you a usable answer. And so you may want to do that low order approximation just so that you can get a nice analytic step response, for instance, in SymPy. If I have time at the end of the lecture, I will also show you that even though you may think that you can easily calculate the roots of a 10th order polynomial, you can't. Not accurately anyway. But all of that has been focused on just taking the function and reducing the order based on that transfer function itself as a function of s. But there's a separate way of thinking about this, which is to say, I don't care about the Laplace transform because I've never seen a Laplace transform on a plant. I've seen tanks and levels and things changing over time, but I've never seen anybody say, oh, you know what, the Laplace transform is getting a bit high. Never happened, right? So why are we even thinking about the Laplace transform instead of just focusing on approximating the behavior of the system in an adequate way, right? If the Laplace transform is really just a way of doing the calculations easier, but we're not interested in the Laplace result, we're interested in the result in time, why don't we just focus on getting the time right? And that is the version that we're going to be talking about next, which is to say we can simply match the response of the system. And there are a couple of rules. The one big rule is that you can easily neglect small time constants. And we spoke about this before. If you have kind of an order of magnitude, if you have 1 versus 10, you're not making a big mistake neglecting the time constant of 1 if there is also a time constant of 10 somewhere in your system. Now I show this directly here. I'm using the control library just because it's easier to calculate, but you can see there, that's what the response looks like. The one is a second order function and the other is a first order function. The one time constant is 10, the other time constant is 1, and you can see that there really you've got to squint. If you guys at the back may not see this, but there are actually 2 lines here, right? The blue line is a little bit slower. It's got that little bit of second order behavior, so you can see that the initial response is the most different, but really we're not making a big mistake, right? So order of magnitude is big for our purposes, right? So that's the Sandrock rule, right? If you have any time constants that are smaller than a factor of 10 away from any of the other time constants, you can just throw away. Just throw away wholesale. No special approximating rule, no nothing. You just draw a line through. There you go. Now, that works okay for functions where we have combinations of big and small time constants. But what if the time constants are all roughly in the same order of magnitude? We can see that the behavior doesn't really change that much. So what I've done here is I've just taken first order systems in series. And you can imagine these to be tanks in series or something like that. You know, so if you think that a first order system is like a tank, then 10 tanks just like one rolling into the other. could be a 10th order polynomial like this. So they've all got the same time constants. We can't easily say, oh yes, that's the problem. We just throw away the one time constant. And you can see there's definitely a family resemblance in that family of curves. They all look very much the same, right? Now, if we look at that, we can kind of say it's starting to look as though that really light blue line, this cyan line, that looks like it doesn't do anything until around 5 seconds, right? And then it looks almost like it's just a second order response, right? So what if we just take kind of a time delay approach and we say, we'll just say that there's 10 seconds of time delay, which is kind of, it's a 10th order function with a time constant of 10, so that's where, or time constant of 1, so that's where we get the 10 from. And you can see that is a reasonable amount of time to wait, but it's not a reasonable time constant anymore, because actually this thing has more slower behavior than just the first order. But you see, we're not actually making that much of a mistake. And we can get quite close. First order plus delay, right? We can kind of just tune it. So we can say, oh, no, that's looking a little bit too fast, that's looking a little bit too slow. We can kind of move the time around. And actually, with not much trouble, we can get very close, I think. That's actually rather near to the behavior that we see, right? Just imagine that that's the full curve that we're talking about. That's rather close. So first order plus dead time is a very popular approximate transfer function because it does describe much high order behavior quite well. Now, obviously, just keep in mind that with the first order plus dead time description, we can never expect oscillatory behavior, right? Why? Because it only has that one real pole. So you need complex conjugate poles to get any kind of oscillation going. So first order, second order plus dead time is also popular if there is some kind of oscillation. And then the final thing that I want to just walk you through is that Skårstad is kind of one of the giants of our industry, wrote the textbook that I use for my postgraduate subject, which is really great. And he is known, he's got two very well-known papers. One is the one where he proposes this approximation, and the other is the one where he proposes very good common sense tuning rules for PIDs. So he's very much about just let's make up some easy rules that work and forget about the math behind it, right? And so basically what he says is, if I've got a big transfer function like this, and I want to approximate that by some lower order transfer function, the first thing I need to do is to figure out how many of these terms am I going to keep. And we're going to just do this as a second order plus dead time approximation. So we're going to keep, first order plus dead time. So we're going to keep that leading term. We always try and keep the largest time constants. That's obvious, right? But then what do we do with the lower time constants? Skårstad proposes this rule. So he says, the first one, the largest neglected time constant, you split halfway between dead time and time constant. And we saw that kind of idea was already there in that previous assumption that I made, where I just said, well, it's 10 systems, they've all got a time constant of 1, maybe they've got a delay of 1, and it worked not bad, but it didn't make the function slow enough. And so Skårstad says, no, split halfway. Half of the time constant goes to the time constant, and half of the time constant goes to the dead time. Then the remaining ones, we add that straight to the dead time. So all the remaining time constants we just add straight to the dead time. And when we work that through, we get a really great approximation of that step response. So this is an easy to apply rule, and notice that it's built to approximate the step response well. Again, you'll notice that it's not trying to be equal to the step response at any particular value. It's trying to get close. Now we're going to do a little bit of approximation stuff in the TUT tomorrow. It's going to be mainly based on the TC lab. I'll try and have it available before the end of the day. but you're going to have time in the session to work with these approximations. You've already played around with it a little. We're going to move into the next study theme as well, because you're going to have data. You're going to gather a lot of data, because the whole of the next study theme is all about identifying transfer functions from data alone, because that's kind of the next obvious step, right? So far we've just done the math, taken first order or taken first principles models and gotten transfer functions from them. What if we didn't need to do that in the first place? What if we could just go onto the plant that exists, gather data, and then propose a transfer function model without ever thinking about mass and energy balances? Wouldn't that be nice? It is nice, and it's the most widely used modeling method in industry. We're going to learn about that in study theme 6, and we're going to start with study theme 6 kind of in the touch tomorrow.